Good morning. We have today uh, the master thesis of Bianca Hazt. In this master thesis, we divided this process in 4 steps. The first one is the raw presentation of Bianca that will spend like 15 minutes for this part. In the second part, we have the questions to the candidate. So we will ask the committee to perform questions to the candidate in this step and to evaluate the ability of the candidate to answer these questions. In the third part, with the committee and the supervisor acting here as the president, we move to another room and we will evaluate deliberate about the quality of the defense. In the fourth part, we return to this room to communicate to the candidate and audience about the final decision. So I will remove all the other members from this screen. Uh, um, just one thing, another thing, an extra thing. I would like to say thank you to Professor Anwesha from Leeds University and to Denise Petri from USP and Professor Eduardo Lemos de Sá from UFPR that accept to participate as a member of this master thesis committee. Thank you very much to all of you. Bianca, now the stage is yours. So we can just manage your time and do the presentation in 50 minutes.
Okay, can you share my screen, please, with the other people? So are you seeing my camera and my screen, my slides?
Yes, is everything okay, Bianca?
So I will start my presentation now. Hope it's everything all right. Good morning and good afternoon too, because we have 2 time zones here. My name is Bianca Hazt, and for my master's thesis defense, I'll be talking about the effect of pH and beta-LACTOGLOBULIN particle morphology on stabilization of amylopectin and Xylo Glucan emulsions. I have been supervised by Professor Hilton Alves de Freitas in the graduate program in chemistry at the Federal University of Paraná. I would like to thank Professor Anwesha, Professor Denise, and Professor Eduardo for accepting to evaluate and to contribute to this work. If you have any problems during my presentation, for example, if your screen is locked in just one slide, I will ask you to write on the chat. This way, Professor Hilton can unlock your microphones and we will see how to solve this problem. Here's a brief summary of my presentation. First, I'll make an introduction on the subject of emotions, and I will introduce a particular type of emotion, the water ones. After that, the material and methods will be presented together with the results and discussion. And at the end, we'll have a brief conclusion, and I will present some further investigation. The first introduction made is the one of emotions. According to the International Union of Pure and Applied Chemistry in the reference cited here, the emulsions consist of colloidal systems that have droplets of one liquid dispersed phase in another. These are called the dispersed and the continuous phase. For this to happen, these liquids must be immiscible or at least partially miscible. And here we have the example of a water fraction, which in the presence of an oil fraction leads to the formation of two immiscible phases. Between the two phases, we have the interfacial tension that appears as a result of the cohesive forces between the similar molecules, which are greater than the adhesive forces. And this leads to a resultant force, which is perpendicular to the interface, and this force is related to the interfacial tension that is represented by a gamma. With that, we have emotions, We have different types of emulsions. The first reported were those formed by oil and water, and there are also emulsions formed only by two oil phases or only by two aqueous phases. More complex emulsions are also reported in the literature, such as multiple emulsions, for example. When the two initially immiscible phases are stirred, an emulsion is formed. In the emulsion formation process, there is a significant increase in the contact area between the two phases, and this increase is due to the formation of the droplets. This increase is represented here by delta A. When there is this increase in the area, the interfacial tension in the system, which is represented by a gamma, acts trying to reduce the area of contact between the two phases in order to reduce the free energy of the system, which has increased. The entropy term undergoes a slight increase due to the fact that one of the phases becomes a dispersed phase. However, the gain in the entropy term is not significant enough to overcome the term represented by the variation of the interfacial contact area multiplied by the interfacial tension. We have that emulsions formed by oil and water are thermodynamically unfavorable systems, and this happens when in the absence of stabilizing agents. The phase separation process occurs due to the need for a reduction in the interfacial area and the extinction of dizzy curved surface of the curved droplets that are formed. And we have some phase separation processes that are observed. Some of them have a thermodynamic origin, while others occur due to the gravitational force, such as, for example, sedimentation and creaming, which occur due to the difference in the density of the dispersed and the continuous phase. An alternative for the stabilization of these emulsions is the addition of surfactants that adsorb at the interface and they reduce the interfacial tension, or of Hampstein-Pickering particles. Hampstein was the first to observe this phenomenon in 1904, and Pickering was the one who reported and explained this phenomenon in 1907. And these Hampstein-Pickering particles, they adsorb at the interface formed by the two immiscible phases, and depending on the wettability that this particle has for each of the phases, it will make a specific theta contact angle, and here it is measured in relation to the water phase. So if you know the value of this contact angle together with the particle radius and also the interfacial tension between the two phases, you can obtain the value of the desorption energy needed to remove the particle from the interface towards one or other phase. Another type of emulsion is the water-water emulsions. These water-water emulsions consist of a mixture of two polymers that are both hydrophilic, but they are thermodynamically incompatible with each other. Two types of phase separation can occur. The associative phase separation process happen, or the segregative, they happen depending on the repulsion or on the attraction between the two hydrophilic polymers and the water, since the water is the solvent here. These mechanisms of phase separation, they are represented here. The associative phase separation generally occurs when two oppositely charged polymers are mixed. These two polymers, they aggregate and form a complex, and the phase separation occurs with one of the phases rich in the complex formed by the two polymers, which generally sediments, and the other phase containing low or no concentration of polymers. In the segregative phase separation, the interactions between the polymeric chains of the same type are favored than the interactions between the different polymers. So this phase separation happen and each of the phases is enriched with one or another polymer. Since these mixtures they present phase separation at certain concentrations, it's possible to build phase diagrams for these mixtures. The general form of a phase diagram for polymers that separate phase in a segregative way or in an associative way is represented here, and I will explain a little more about this one, the segregative phase separation, because it's the one that we use it in this work. So for polymers that undergo segregative phase separation, the expected phase diagram has the form shown here. It's quite common for this representation of this ternary phase diagram to be performed only in 2 axes instead of 3. Here we have 3 axes, so this is very common because the water phase is a common solvent between the 2 other polymeric fractions. And in this phase diagram here, we have the values of the 50-50 line before the phase separation. These values are plotted together with the equilibrium concentrations after the phase separation has happened. And the tie lines, they are represented here connecting both these concentrations, the 50-50 line and also the concentration after the phase separation. These tie lines, they converge together at a critical point. In this critical point, the 2 immiscible phases merge and become just one single phase. Here we have the macroscopic monophasic region, while here we have the macroscopic biphasic region, and what separates them is the binodal line. When these emulsions are in the absence of other agents that modify the type of emulsion, it's very likely that the type of emulsion will be defined by the polymer with the highest volumetric fraction. These phase diagrams also present some very interesting properties. For example, a constant interfacial tension along the tie line, regardless of the concentration used. And there is also the condition of the parallelism of the tie lines, which is observed when the phase separation is complete and also it's in equilibrium. The biphasic region appears precisely when the concentration of both polymers is increased and the enthalpy of mixing overcomes the entropy, since the entropy of mixing is negative. The construction of these phase diagrams is also essential for the identification where the phase separation occurs of the region that the phase separation occurs. And when working with water-water emulsions, the phase diagrams are really important because some variations in the chemical composition and also in the molar mass of the macromolecules, they can generate some different phase diagrams. Like the oil in water emulsions or water in oil emulsions, the water-water emulsions also require agents to stabilize them so that the phase separation does not happen and the emulsion remains stable. In the particular case of water-water emulsions, the addition of surfactants or amphiphilic molecules is not an alternative for the stabilization of these systems, since the water-water interface is not as defined as the interface of emulsions formed by oil and water. This fact here is evidenced by the interfacial tension, which for systems formed by oil and water has values close to 30 millinewton per meter, while for water-water systems, the tension values commonly found in the literature are in the order of 10 to the power of -2. The surfactants are then not effective in stabilizing water-water emulsions. A good alternative is the addition of Hampstein-Pickering particles, and these particles must be a few nanometers in size so that they are able to absorb at the interface and stabilize these emulsions. Here I brought a timeline with a few articles on the topic of water-water emulsions. The first report of phase separation between hydrophilic polymers was in 1986 by Benjamin. This author observed the formation of droplets when mixing starch and gelatin dispersions. And since the scientific discoveries are usually unintentional, this author wasn't investigating the phase separation between two hydrophilic macromolecules. He was actually studying the growth of bacteria in starch. And however, he managed to discuss that the type of emulsion depended on the polymer fraction used, and also that the droplets size varied according to the agitation of the system. In 1997, Greenberg reported that water-water emulsions are formed due to the thermodynamic incompatibility between certain combinations of hydrophilic polysaccharides. In 2014, Trump published an article that evaluated the profiles of water interfaces, and in here he evaluated the composition, the concentration, and also the charge profiles, and the charge was for the case of phase separation between neutral and weakly charged polymers. In 2016, a very complete review was published about water-water emulsions. This review showed different systems and ways of stabilization with some perspective for the application of these materials. In 2019, Dickinson published another article, and it was an extensive review about biopolymers-based water-water emulsions stabilized by particles. In this timeline, I brought a little about the stabilization of water-water emulsions using different materials. In 2008, there was the first report of the interfacial adsorption of particles in different emulsions by Purification. Here, different particles were used in different solutions of two polysaccharides or one polysaccharide and one protein. In 2012, Balakrishnan published about the adsorption of latex and protein particles also at an interface formed by polyethylene oxide and dextran. The latex particles were relatively large. They had around 1 micrometer, which allowed the measurement of the contact angle and also the calculation of the adsorption energy of the particle at a water-water interface. In 2014, another paper was published talking about the influence of the protein particle morphology on the stabilization of water-water emulsions using model polymers, which were again PEO and dextran. In 2016, in the first work of Biopol within water-water emulsions, Freitas used protein microgels in emulsions of amylopectin and jatobá Xylo Glucan. That's two hydrophilic polysaccharides that lead to the formation of water-water emulsions. The two materials that were used here to form the water-water emulsions that will be presented in this work were also the polysaccharides amylopectin and Xylo Glucan. I will start with the amylopectin structure. It is the major component of starch, and together with amylose, it forms a material that has nutritional and industrial importance. And the amylopectin chain is highly branched, and it consists of alpha D glucose units with 1 to 4 and also 1 to 6 glycosidic bonds interconnected to the main chain. The Xylo Glucan was the other material used here. It's a shortly branched material. Sometimes it's also called a linear polysaccharide because of just some branches that it presents. And it's composed of beta-D glucoses with 1 to 4 linkages, and it has some substitutions at the O6 for alpha-D xylose. And this alpha-D xylose has occasional beta-D galactose units on the O2 of xylose. Currently, the Xylo Glucan obtained from Tamarindus indica, which has a name of tamarind, is used in the food and also in the pharmaceutical industry as a thickener agent because it's able to form viscous aqueous solutions. It's a polysaccharide that behaves as a water-soluble fiber, and so it's not digested, and it's it has some applicability in dietary foods. To stabilize the emulsions of amylopectin and xyloglucan, an alternative is the addition of particles that are also a part of the food grade. The protein used in this work was beta-LACTOGLOBULIN, which is one of the major proteins of WPI, which is the whey protein isolate. That's the soluble fraction of whey from ruminant species. And this protein has an isoelectric point of 5.2. When this protein is heated, it undergoes a process of denaturation, and some intermolecular interactions give rise to aggregates that form irreversibly. It's also reported that when the reaction conditions are varied, the particles produced from beta-LG may present different morphologies. For example, when heating this solution of protein at pH 5.2, and that's the value closest to the isoelectric point, the particles produced have a spherical shape and they are called microgels. When at higher pH, but in the presence of a salt such as calcium chloride, larger and more stable microgels are also formed. Under pH conditions between 2 and 3, the protein forms nanofibrils with a rigid structure. At a higher concentration of polymer and also above the isoelectric point of the particle, this protein forms aggregates with the presence of ramifications, and these aggregates are also known as fractal aggregates or just fractals. In this way, after this brief introduction, the general objective of this work is to develop water-water emulsions based on polysaccharides, like this one represented here on the slide, where the slighter denser phase sediments of amylopectin and the xyloglucan creams, and to evaluate the stabilization of these emulsions with the addition of protein particles with different morphologies. For this, some necessary experimental steps include the purification and the characterization of the materials, the construction of phase diagrams, also the synthesis and the characterization of protein particles, and also the evaluation of the stability of the emulsion in the presence of the protein particles. Here I brought the summary again just to point out that the material and methods used in the work in each experimental step will be presented together with the results and discussion. For a better understanding of the work, they will be presented together. The first experimental step of the work consisted on the purification of the polysaccharides that were used. The first purification performed was the one for xyloglucan, and actually we used three xyloglucans, and the first one was the xyloglucan 1. It was initially used. This material was purified from TKP, which is the tamarind kernel powder. That's a tamarind seed powder that has a high concentration of xyloglucan. This TKP was donated by an Indian company. It's a commercial material and it's used as a thickener. In order for this material to be used, it was purified. In order to extend the work to other xyloglucans with possible different macromolecular properties, two new sources of xyloglucan were used to continue this study. So as a result, some tamarind fruits were purchased at the Curitiba city market, and these seeds, they were isolated, as I will describe later in this slide. And this material called Xyloglucan 1 was first extracted and then purified. The third xyloglucan sample consisted of a commercial xyloglucan donated by a company in Japan. According to the tag of the commercial sample, it's not a TKP like the Xyloglucan 1, but it is the isolated xyloglucan itself. Even so, before using this material, it was also purified. The extraction process was carried out only for Xyloglucan 2, and that's the one in which the fruits were purchased at the Curitiba city market. So initially the fruits were manually peeled and boiled for 30 minutes so that the enzymatic inactivation of the seeds occurred and the cotyledons could be completely separated. Then these seeds were dried and crushed, and the delipidification was performed in a Soxhlet extractor using hexane as a solvent for 48 hours, and this was the homemade TKP. It was obtained at Biopol, and then later this material went through the purification process. The purification was then performed for 3 samples, Xyloglucan 1, 2, and 3, and first, for the purification, each one of the materials was dispersed at a concentration of 40 grams per liter, and this dispersion was stirred for 12 hours. This sample was centrifuged and the material was filtered, and the supernatant was then precipitated with ethanol. The purified material was separated and washed extensively with 99% of ethanol and also acetone. This photo is one of the 3 samples. I think it's from Xyloglucan 3, but it is representative for the 3 purified Xyloglucans. They were fibrous and also white in their appearance. The samples, Xyloglucan 1, 2, and 3, were characterized by size exclusion chromatography, and the dilution profile for each one of them is represented here. The Xyloglucan 1 is the sample that has the lowest molar mass among the 3 samples, and the dispersion values for all the samples are characteristic of polydispersed polysaccharides, that's 2.4, 2.8, and 2.0. It can also be seen that the weight average molar mass of Xyloglucan 2 is 15 times greater than the one of Xyloglucan 1, while the molar mass for Xyloglucan 3 is 26 times greater than Xyloglucan 1. An extraction step was also necessary to use the amylopectin. Actually, here it's called a purification. The amylopectin was dispersed in a mixture of dimethyl sulfoxide and water at a concentration of 50 grams per liter, and this was kept under magnetic stirring for 48 hours. After the centrifugation, the polysaccharide was precipitated using 3 volumes of ethanol, and after the centrifugation again, the purified amylopectin was washed again and then dried. Before the purification process or the extraction process, the amylopectin elution profile suggests the presence of other populations of polymers because the peak is not symmetrical. It presents a shoulder peak here, which was observed in all the detectors. After the purification process, this shoulder peak does not appear as before, and also the percentage of recovery of the concentration of the polysaccharide that was injected into the sac equipment, it increased from 24.8% to 74.1%. Considering both the greater symmetry observed in the elution profile of purified amylopectin and also the increase in the polysaccharide recovery after the elution, it appears that the process used for the purification of this sample was efficient for removing other molar mass fractions that were present in the sample. The whey protein isolate has some other proteins besides beta-LACTOGLOBULIN, such as alpha-lactalbumin, and in order to isolate this fraction, the WPI was dispersed in purified water at 100 grams per liter in the presence of sodium azide in order to avoid bacterial growth. This mixture was kept under constant stirring for 24 hours, and after changing the pH to 4.2, this dispersion was centrifuged. The supernatant was removed and dialyzed against water, and the final material was removed from the membranes, and it was frozen for later lyophilization. After the purification that was previously described, the purified whey protein was analyzed by size exclusion chromatography. After the solubilization of this material in the mobile phase, the SEC elution profile can be observed here. It's observed that this material, this purified WPI, has a population of 95% of beta-lactoglobulin and 5% of alpha-lactoglobulin, and therefore from now on it will be called only beta-lactoglobulin. The value of the weight average molar mass determined by size exclusion chromatography was 2.8 times 10 to the power of 4. This value represents the balance between the protein in its monomeric form and also in its dimeric form. After the purification to obtain the protein particles, the purified WPI or beta-lactoglobulin was slowly dispersed in purified water at a concentration of 100 grams per liter. After 12 hours of agitation, the solubilized material was centrifuged and the supernatant was separated, and the concentration of the protein was determined by spectrophotometry using a non-extinction coefficient from the literature. From this concentration that was determined here, the preparation of the protein particles, for the preparation of these protein particles, the beta-LG was diluted to a concentration of 40 grams per liter, because this is the concentration in which the particles are prepared. For the protein particles called microgels, the pH of the sample was adjusted to 6.9 and the mixture was heated in the presence of calcium chloride. For the fibrils, the protein dispersion at 40 grams per liter was heated at pH 2 with magnetic stirring for 5 hours. The characterization of the particles is shown here in terms of the morphological aspect that they present. I mean, the microgels have a spheroidal morphology, while the nanofibrils are particles with a higher aspect ratio. They are rod-like particles. And the images shown here are from atomic force microscopy for the microgels, the radial that was determined by scanning electron microscopy was 91 nanometers, and it is a smaller value than the one obtained by dynamic light scattering, which was 184 nanometers, because here the sample in the microscopic analysis is dried, and also this specific microscopy is done in high vacuum. The morphological aspect of the nanofibrils is also shown by atomic force microscopy, and the estimated diameter is 40 nanometers. And when measuring the height of the samples, the values that were found were close to 5.6 nanometers, and this size is closer to what is found in the literature. It's likely that this is the right value because measuring the sample height avoids the tip convolution effect, which makes the images appear wider than they really are when the tip size is close to the size of the sample. The protein conversion to microgels or nanofibrils was measured by centrifuging the materials and quantifying the residual protein in the supernatant. For microgels, the conversion was 84%, and for the nanofibrils, 46%. The phase diagrams that were built by me were for the materials Xylo Glucan 2 and 3. The same methodology was previously adopted in our research group for the Xylo Glucan 1, as I will present in a minute. So initially, The emulsions with composition in the 50-50 line were prepared with these concentrations at this table, and the quantification was performed by size exclusion chromatography and also by volume fraction measurements or height measurements. For this, the upper and the lower phases were gently removed from each tube of this table that presented phase separation, and these samples were removed, uh, diluted to a theoretical concentration, and filtered and injected into the size exclusion chromatography equipment. This was performed for each of the upper and lower phases, as I said, and the tie lines of the phase diagrams were drawn based on the two concentration values that were calculated. The first is the concentration that the size exclusion chromatography provided, and also the concentration calculated by the height or volume fraction measurements. Later, other emulsions were prepared in order to find the position of the binodal line. This phase diagram for Xyloglucan 1 had been constructed previously following the same methodology that I just presented by Bassani in her master thesis, and this is the phase diagram for Xyloglucan 1, which has a lower molar mass, and the emulsions that I will present were prepared at the concentration indicated by the red dot, which represents a concentration of 1.03 to 1.3 of amylopectin in xyloglucan. For all the materials, the phase separation was complete even for the highest concentration that were used here, and this profile was identified by SEC. With the three diagrams placed side by side here, it's observed that for Xyloglucans 2 and 3, they have greater molar masses than the Xyloglucan 1, the lines that connect the concentrations of the 50-50 line, they present some similar inclinations. And since the parallelism condition here is maintained, it can be said that the measurement of the concentration was carried out in an equilibrium concentration between the phases. Since the molar mass increases when passing from the phase diagram with Xyloglucan 1 to 2 and or 3, we have a lower entropy of mixing that leads to the formation of biphasic regions at lower concentrations. So this can be observed in the graphs, since for this Xyloglucan we have a bigger monophasic region. So, as I just said, the emulsions that I will present here were prepared in this proportion. In order for the emulsions stability to be evaluated, the emulsions were prepared by weighting the amylopectin phase followed by the xyloglucan and a certain amount of water to reach the desired point in the phase diagram with sodium azide as a conservative. The nanoparticles were added to the emulsions at a concentration of 1 weight percent, and the last step was to adjust the pH using hydrochloric acid or sodium hydroxide until the desired pH. The final appearance of an amylopectin and xyloglucan emulsion is here, and the emulsions were evaluated both macroscopic and using by acquiring images in a confocal laser scanning microscope. The first result that I will present is the one of amylopectin in emulsions in Xyloglucan 1. These emulsions were evaluated in the presence of microgels and nanofibrils, and initially I will compare the effect of the stabilization of these particles in these emulsions. So here we have the emulsions in the presence of 1% of protein microgels after 1 hour of rest. It's interesting to note that emulsion is formed even at the highest pH, evaluated at pH 7. However, there is no presence of protein particles at the interface between amylopectin and xyloglucan, and the alarm at pH 7 and the enlarged images show this difference. Here we have the same emotions as the last slide in the presence of 1% of microgels, but after 24 hours of rest. And these are very interesting results because they show that the phase separation occurs normally for the case of particle-free emulsions. And although at pH 7, a small fraction of amylopectins appears sedimented, all the emulsions show some stability when compared to the negative control, which has no particles. And this stability is better understood when we observe the confocal images. We have that at pH 5 or greater than 5, we observed some deformed morphologies, and this indicates a gelled network that was formed. This gelled network is confirmed when the tube is inverted. This test was supposed to be a tilt test, and that's a test in which you tilt the tube and check how much the emulsion flows. You tilt the tube at a specific angle, for example. And since the emulsion did not flow, the tube ended up being completely inverted, and the emulsion supported its own weight for a few minutes before the gelled network was broken and the emulsion flowed. At pH 4, the emulsion is mainly stabilized by the Pickering effect. In this short video that shows a slice of the emulsion formed by the superposition of several images that were acquired in Z, this emulsion is at pH 4, and after 24 hours of rest, it shows that the stability of the emulsion in this pH is largely due to the Pickering effect, because after 24 hours, the coated droplets are still present, and the coating of these droplets appear uniform at any region that is observed, as this video shows. The emulsions that were prepared here are using the same Xylo Glucan and at the same point of the phase diagram, but not with microgels anymore, with nanofibers. So the first images are taken here after 1 hour of rest, and again, the existence of emulsified phases is observed for all the evaluated pHs, and there's a more evident droplet coating at pH 4, and there's a less evident but still existing at pH 7. When analyzing the emulsions of the previous slide after 24 hours of rest, it's observed that at pH 4 some droplets appear with deformed morphology. However, there is still the presence of particles at the interface at pH 4 and at pH 7. The confocal images of the emulsions in the presence of microgels and nanofibrils are here for a brief comparison. These emulsions have their pH ranging from 4 to 7, and it's possible to observe that the coating of these droplets in the emulsion is more effective for microgels at pH 4. However, above pH 5, the microgels do not appear at the interface, while the nanofibrils appear in a thin layer covering the droplets of the dispersed phase, which is amylopectin. This effect is mainly observed at pH 5 and 6, and here the fibrils cover the interface, while microgels appear to do not. The emulsions with Xyloglucan 2 and Xyloglucan 3 were also evaluated in the presence of microgels and nanofibrils, and in this presentation I will only show the stabilization effect for the Xyloglucan 3 at the same point previously studied for the Xyloglucan 1 emulsions. The pH of the sample was adjusted in the range of 4 to 7, And the emulsions without particles remained stable even for a longer period of time than the Xyloglucan 1 emulsions did. And that's because of the higher viscosity that these samples present. When performing the tilt test here, and that's the test in which the tube is tilted, it was verified that there was a significant increase in the viscosity of the emulsions in the presence of particles. However, this gain in the viscosity was not high enough for the emulsion to maintain its own weight for a few moments, like what happened to the emulsions with Xyloglucan 1 that had the lower molar mass. Macroscopically here, it can also be noticed that the emulsions at lower pH values remained stable for longer periods of time with nanofibrils than with microgels, since the emulsion sedimentation occurred slower for example, at 81 hours with nanofibrils. This happened also at higher pHs, evaluated 6 and 7. Previously, with the xyloglucan, the behavior of fibrils and microgels in the interface depended on the emulsion pH. Here, this effect was reproducible for the xyloglucan 2 and 3. Here I show the xyloglucan 3 that has a greater molar mass. Since the nanofibrils placed themselves at the interface at pH 6 and 7, while the microgels did it only at pH 4 and 5, we came up with an idea to mix both particles at the same emulsion. So here we have an emulsion with both microgels and nanofibrils at 1% weight percent. And this result was quite interesting because it shows that the emulsions were stable for longer periods of time. Because without the mixing of both particles, the phase separation had already started to happen at 81 hours, for example, while here at 196 hours, the emulsions were still stable. And in the confocal images, it can be noticed that at pH 4 there is a thick layer of microgels and also nanofibrils at the interface, while at pH 4, for example, the fibrils place at the interface, while the microgels prefer to interact with the amylopectin phase, although some fibrils might interact with the amylopectin phase too. Our last test that we tested were the evaluation of the repulsive potential of both the particles, the microgels and the nanofibrils. By adding sodium chloride at 0.01 mol per liter to the dispersion of the particles, it could be noticed that the potentials were screened of the particle. So the isoelectric point did not change significantly from the ones observed in water, although when performing this titration several times, we observed a slightly different variation when in the presence of sodium chloride. And since in the presence of sodium chloride, the repulsive potentials of the particles were screened, we decided to evaluate the emulsion's behavior in the presence of sodium chloride. Macroscopically, there was no significant changes on the behavior of the emulsion, but in the confocal images, it can be noticed that there is a thicker particle layer adsorbed at the interface for both particles, and this forms a rigid structure that is due to the absence of the repulsive potentials that once existed in the absence of salt, especially here in the case of nanofibrils. For the microgels, again, the adsorption effect by the Pickering mechanism is more pronounced at lower pH values, as the droplet zoom here shows. For higher pH, for example 6 and 7, the microgels, they interact preferentially with the amylopectin phase. Based on what was presented here, the first conclusion is that the nanofibrils show it to stabilize the emulsions under conditions not previously observed for spherical particles, and this was evaluated for emulsions with Xylo Glucan 1 in amylopectin. This result was published in the journal Food Hydrocolloids. Since the microgels had stabilized the emulsions at pH below or equal to 5, while the fibrils had stabilized the emulsions with pH up to 7, mixing both spherical and rod-like particles was a successful approach to stabilize the emulsions. Another conclusion is about screening the electrostatic interaction between the particles, and this showed the influence of the particles' charge, negative potentials on the amylopectin and xyloglucan emulsions. Without the repulsive potentials, the particles formed a thick layer at the interface and stabilized the emulsions. So, when evaluating amylopectin emulsions in Xyloglucan 1, 2, and 3, it was noticed that the molar mass effect is quite significant on the stability of the emulsion as well as on the phase diagram, because this scheme shows that with lower molar masses, higher polysaccharide concentrations were required for the phase separation to happen. Also, the phase separation happened faster because of the lower viscosity that these samples have. When dealing with higher molar masses values, some lower concentration values were needed for the phase separation to happen, and also the phase separation took longer to happen, and this is due to the higher viscosity. Despite the effect of the molar mass presented here, the behavior of the Pickering particles stabilizing the emulsions under different pH conditions was universal regardless of the molar mass that was used. Some further investigation is now presented. It's intended to analyze whether the particles migrate to the interface when changing the pH at the time of the confocal microscopy analysis, and this could generate some interesting results. It's also intended to compare the effect of molar mass on the rheological behavior of emulsions. We already have done some trial tests on that, and it seems that the interaction of microgels and nanofibrils happen not only with the xyloglucan but also with the amylopectin phase. And this makes sense because when we observed some confocal microscopies, we could see that sometimes the protein particles placed themselves at the amylopectin phase, depending on the pH. It's also intended to investigate the effect of changing the isoelectric point of the particles on the stability of the emulsion, and to write a scientific article for the publication of the last results. This was my presentation. I would like to say thanks to my supervisor, Professor Hilton, who taught me so much about scientific research, about dedication, and also for being someone who inspires me every day. He has a critical way of thinking and acting that inspires me really much. And if I could go back in time, I would have asked you again and again and again to get a place at Biopol. I would also like to say thanks to Professor Anwesha, to Professor Denise, and Professor Eduardo, who accepted the invitation to evaluate and to discuss this work. Also to my colleagues from the Biopol lab. I cannot leave this photo behind because since I only used the tamarind seeds to isolate the xyloglucan, you guys helped with the pulp of the tamarind fruits. This picture was right before the pandemic started. And from Biopol, I would like to say special thanks to Franciele, who is a great friend. I would like also to say thanks to the University Microscopy Centers, that's the Center for Advanced Technologies in Fluorescence, and to João Luiz in there, who helped me with the confocal images, and also the Electronic Microscopy Center, to the funding agents, CAPES and CNPq, and that's the They are who financiate the scientific research here in Brazil and also to our partner companies, MC Química, Boticário, and Next Chemical. I would like also to say thanks to my family, Adriana and Ajir, who support me always, even from far, and to Beatriz, my sister, and Pedro, my boyfriend, who support me closely. To everyone who is watching, thank you.
Thank you very much, Bianca, for your very nice presentation. Thank you for the acknowledgement. Thank you very much. And I would like to invite Professor Anwesha Sarkar to contribute with the work. So, Professor Anwesha.
Hi, Bianca. Congratulations. This is a very good piece of work. So, what you have done is super comprehensive, scientific, and adds to the state of art, which is very useful. So, if I understand now, my time starts to ask you some questions. So, what I will do is I will go through part by part, like you did in your presentation and your thesis.
Mhm.
So let's start with the first, your rationale. So you said that you want to use these two kinds of particle to stabilize the system, but at the same time you know the interfacial tension is very different, is super low in water and water system. So you said you cannot use surfactant and you want to use particle. Can you just explain how particle can help there? Why particle is useful to increase the, let's say, the stability of these kind of emulsions?
Sure. I will ask you, and if you're not satisfied with my answer, you can ask me the question again, okay? So, first, we decided to use spherical particles. We even tried fractals too. I showed in the presentation that they can also be formed by heating the protein. And the effect of stabilization using fractals and microgels was quite similar. So we decided to use another particle which had a different morphology, and we observed different stabilization for these both particles. The reason why we decided to use these particles is because there is another mechanism of stabilization of these emotions, which is the addition of copolymers. I think I mentioned it in my written document, and uh, we still didn't try it for amylopectin and xyloglucan. I imagine that it's a kind of a hard work to make copolymers from natural polysaccharides, but it can also be tried. And we decided to use protein particles to stabilize the emotion because they seem to be the easiest way. I mean,
Yeah.
the
Now,
first.
my question was a slightly bit different, and even not thinking about protein particles, even just thinking about particle.
Mm,
So you highlighted the the equation of when you use a particle, you get much higher, let's say, desorption energies and stuff.
mhm.
So my question to you is really what is the benefit? So in water in oil or oil in water emulsion, I can see the benefit. But in case of water in water emulsion, what is the benefit of using particle?
I guess now I understood your question, and I think the answer would be that first, about 15 years ago, I think there was an article that talked about that the stabilization of water-water emotions happened due to the fact that at the interface of the droplet of one polymer with the other, there was less polymer concentration. There were more water. It was a solvent-rich interface. And then the particles migrate migrated to the interface, because there they would be still under Brownian motion and it would be easy for them to stay there. So this is why water-water emulsions presented Pickering effect. But there's a recent article that I read that discussed this effect, and even water-water emulsions having much lower interfacial tension values, it seems that there also is a reduction in the free energy of the system due to the reduction in the interfacial tension when the particle is absorbed at the interface. So there is this discussion in the literature, but I do believe that even being lower and lower interfacial tension than when compared to oil, water, and water emulsions, the stabilization effect is probably due to the reduction in the interfacial free energy of the system.
Mhm. So, related to that, my other question is, if you again go back to your equation, so here we are talking about protein particles, and when you have two different kinds of immiscible phases, then it's very easy to use protein particles because their wettability is very different in the different phases. What is your interpretation about using protein particle when you are using xyloglucan and starch? Both are hydrophilic polymers, and you are using protein. Do you believe that the protein particle will have different kind of wettability in this two system? I know you have not measured it, but I'm just trying to understand your understanding. So do you believe these particle will have different kind of wettability or partitioning to the xyloglucan and to the amylopectin phases?
Yes, I do believe that the partition coefficients are probably different of each particle with each interface, and it also seems to depend on the pH that the system is. Because when we can I project my screen to
Yeah,
help me?
yeah.
Just a minute. I don't know if you can see my screen.
Yep.
Yeah, okay. I think this slide is good for what I'm trying to say, because the nanofibrils and the microgels, they seem to interact in a different way with the amylopectin and the xyloglucan. And this is evidenced because the nanofibrils, they place themselves at the interface at pH 7 or at pH 6, while the microgels do not. They interact preferentially with the amylopectin phase. So at this pH, it's certain at pH 6 and 7 that the microgels, they probably interact more with the amylopectin phase, and we are not sure about the reason for that. I think we need to discuss some further experiments to investigate this effect, because they are not charged polymers. As you said, they are both neutral polymers, polysaccharides, and the protein has a charge, and it could be easily explained if we had charged polymers, but we don't. And I performed some experiments trying to see if we could identify some charges at the polysaccharide, but they don't seem to present a charge doing, for example, potentiometric titrations. And the answer for your question is that yes, there is a difference on the partition of the protein particles to the different phases. Here, they interact more with the amylopectin phase, And when they interact with the xyloglucan phase, it seems that they leave the amylopectin phase and go towards the the xyloglucan phase. And in this process, they end up placing at the interface. The nanofibrils probably interact more with the xyloglucan at all at pH 4 to 7, while the microgels probably interact with the xyloglucan at pH 4, while at pH 7 they probably do not, since it's really rare to observe. For example, here, if you can see this image, you cannot see microgels at the xyloglucan phase.
Mm-hmm. Mm-hmm. Good, great. Um, my other question is the choice of your nanofibril and microgel. So, what was your initial hypothesis? First of all, why you chose two kinds of particles? Like, why two different shapes of particle?
Okay.
And what was your hypothesis? Like, did you have any idea from the beginning before doing any experiment that this nanofibril might be better or less better in terms of stabilization as compared to the microgel?
So, as I said, that the disruption energy seems to be an important parameter even with low interfacial tensions. It's expected that spherical particles they have greater disruption energy than the rod-like particles, the nanofibrils, at any orientation from the interface. So my initial idea was that the microgels would stabilize the emulsion in a better way than the fibrils. But this phrase that I said that about the disruption energy, it's only valid when you compare, for example, particles with the same volume. And it's quite hard to obtain particles with the same volume when making, for example, protein particles, né? Né. That's a Brazilian expression, sorry. And I mean, the
So,
initial idea was this, but then we figured out that the nanofibrils, they probably can cover a larger interfacial area because some nanofibrils, they have 2 or 3 nanometers, they are long, they are really elongated, they have a rigid structure. And then we find out that the fibrils had this difference in the absorption at the interface.
mhm, this is exactly what you said right now, correctly, as compared to previously, because you said initially that spheres, your microgel will have higher desorption energy, which is not true because microgel have least area as compared to the area of the nanofibrils. But
Yes.
that is one reason that your cross sectional area will be much higher in case of nanofibrils. So you will have a better desorption energy. Number one, and number two is the packing, because the kind of packing parameter for your nanofibrils most likely will be much higher. You can pack way more particles as compared to the spheres. So yeah, good, good. Now, coming to the kind of data you got on pH, so you saw that the microgel works only at a certain pH, and then you don't see microgel in the interface anymore at pH, higher pH at pH 7 or something. But in the nanofibril, they are pretty good. So they are there and they continue. Why? What is happening? What do you think is going on there?
We have an idea of what's happening. It's not proved yet, and probably that's the next thing that we need to investigate because it was shown before that the microgels they interact with the xyloglucan when they have a positive surface charge. For example, when the pH is set above below, sorry, when the pH is set below the isoelectric point. And the microgels, they have a lower isoelectric point than the nanofibrils. So if the nanofibrils interact with the xyloglucan in the same way as microgels does, probably they having a higher isoelectric point would make them interact with the xyloglucan phase, while the microgels that have a lower isoelectric point do not interact. For that, we aim to change the isoelectric point of, for example, the spherical particles, the microgels, because then we could evaluate this possibility if changing the isoelectric point is really the way to make the particles go to the interface.
Mm-hmm.
And we thought our first idea about making the experiments with the salt by adding sodium chloride was that it would change the isoelectric point of the particle, because sometimes it does change the isoelectric or the ionic point. But this didn't happen in a significant way, although it made the particles aggregate because of the absence of the repulsive potential. So I think this is it.
Mm-hmm. Mm-hmm. That's interesting. Now, when you started mixing the system, again, why did you mix it? Because the point is, with your microgel, you had a much lower pH range to work on as compared to the nanofibrils. When your so I would have only mixed things when, imagine, one works at one pH, another works at another pH. You combine them to see if they work in the entire pH range. But your nanofibril was phenomenal. It was working from pH 4 to pH 7. What was the benefit, or what was the rationale of mixing the microgel and nanofibril? What benefits did you get?
Okay, I will share my screen again. Are you seeing my screen?
Yep.
So we had that although the nanofibrils, they absorb it at the interface at pH 4 and also at pH 7. At pH 4, the microgels, for example, in this Xyloglucan, they were the best alternative, because it seems that a thicker layer of particles is absorbed at the
Yeah.
interface here, for example, while here you don't have that kind of thicker layer. So this is the main reason why we chose to mix both particles. And also because since the microgels migrate to the amylopectin, there are some studies, some recent studies that show that the formation of a gelled system can also occur not only by gelling the continuous phase, but also by gelling the dispersed phase. So this was our idea, to mix both particles in the same emulsion. Yeah, I think this was it.
Yeah. The other question which I have is, you had some gelation in some of the samples, and you said that is due to the Xylo Glucan interaction, but I didn't quite understand. So, in some samples, you got a gel-like structure. Don't you think that the particles had an influence as well?
Yes, sure, because there was another study. Professor Hilton took part on it. He also I will explain a little bit about this, and then I answer your question. They prepared microgels, protein microgels, and they coated the microgels with xyloglucan. So they prepared core shell particles, core shell like particles from protein with xyloglucan. And when they did it, they used another xyloglucan that was a xyloglucan from jatobá seeds, but since they are both similar polysaccharides, they don't have big differences in the sugar units that compose the material. So what they observed is that when they mix it, they prepared a protein, a microgel dispersion, and then they used Xyloglucan to coat these protein microgels. Then they centrifuged the coated protein particles and took the supernatant and analyzed. And what they saw is that the interaction of the microgels with the xyloglucan happened for the lowest molar mass fractions of xyloglucan because they seem to interact preferentially with the microgels. And since in the supernatant they identified only the highest molar mass fractions, it was almost a monodispersed material that didn't coat the protein particles. So this is our initial hypothesis that the interaction happens with a lower molar mass fraction, which was the xyloglucan one. And for the other xyloglucans in which we didn't see any gelation, we think that they don't interact. To test this hypothesis, I have a scientific initiation student who is testing it right now. She's doing the hydrolysis of the xyloglucan using an enzyme that breaks the glucan chain, and she is aiming to test the effect of gelation using lower molar mass fractions and using higher molar mass fractions.
So this brings me to a related question then. So, for improving the stability of a system, you use particles, which is great, to put the particles at the interface. Now, the other approach which can be used is to structure one of the continuous phases. So, by gelling. So either you can use a different system of gelling in case of the xyloglucan, or you can actually use the particle itself to form a structure in the bulk phase. So did you see any of your particles or your nanofibrils what you have used to form any structure in either of the bulk phases rather than at the interface?
Yes, we saw for the xyloglucan that had the lowest molar mass
Hmm.
because they seem to interact with the protein particles, especially the microgels.
Hmm.
And I will share my screen again. Just a moment. I don't remember where, I think it's here. And we could observe, for example, here in this image, where we observed this gel formation, we observed what seems to be a gelled network because the droplets, they seem deformed. They are not spherical droplets. And I guess this is a characteristic of a gelled, not a gelled structure because the droplets are deformed. And also you can see
The network.
a jellified structure in the
Yeah.
continuous phase
Yep.
of the particles at the continuous phase. So we guess that's what's happening here for the microgels with the
Fantastic. And
xylem.
and you don't see such kind of behavior with the nanofibrils,
No. This gelation is not that strong with nanofibers.
which is pretty interesting, no? It is worth to explore that because, of course, not with you, your master's thesis is done, but it's quite interesting area to understand because for me it's very important to understand the real contribution, whether it's real, true particle stabilization at the interface or whether particles are being used as structuring agents in the bulk phase. Although you're getting stabilized material, but at the end of the day, what is the true mechanism. And I think it's very important to understand. And that kind of brings to my last question. Um, Two questions connected. So, first is, you have used a FEM to measure the size and so on of these particles, which is great. Um, do you think doing work on understanding this bulk phases a bit better using rheology will be helpful when you try to really measure the material performance of this material? That is my question number one. And question number two is, all of this work what you have done, what do you think can be potential application?
Okay, so the first question I didn't quite understand. It's about how could I measure the structuring of the gel and these kinds of
Yeah.
things, right? Okay, so I guess rheology is the best answer for that. We could start mixing both particles, first fibrils and then microgels, setting the pH only with Xylo Glucan and then only with amylopectin, and measuring if there are any difference between the viscosity, for example, or the two modulus of the samples. And the second question was about the application of these systems. And I guess there's a lot to investigate before this comes, this time has come, because, for example, if we think about foods and to put dizzy water emotions in our mouth, there are many things um, that could interact there, because, for example, the enzyme that promoves the degradation of amylopectin is in our saliva, I think.
Mhm.
That's amylase. And I don't know if, for example, amylopectin is the dispersed phase in the emotions that we evaluated. I don't know if how they would interact. So maybe some rheological tests could be done with that to observe if there is a difference in the viscosity of the sample under different conditions, and there's a lot to be investigated before these emulsions are actually applied.
Mhm.
But I think we made a good path until here, because we investigated the behavior of these protein particles. And but for the application, I guess we would have to do a lot of more experiments.
Very good. Thank you very much. From my end, I'm good.
Professor Anwesha, Sarkar, thank you very much for your questions. They are really appropriated. We're really happy with your presence here. I think Bianca is really happy to be in contact with you. Thank you very much again. And I would like to invite Professor Denise Petri to contribute with the discussion.
Hello, thank you very much for the nice presentation, Bianca. Also, your master thesis is also very nice, so we can observe that you learned a lot and you worked with many different techniques. It's very important for your formation. Yeah, so it's really appreciated to read your work. And also we see that it's a very nice, a very high quality work, because you have already a paper published in a top journal on food science. So congratulations. And but I played the role here to ask something. So I must ask something, and I would like to go through the basic concepts as Professor Anwesha did, I'd like to start from the fundamental points. I do not understand why this label, water emotions, appeared. Because when I read about it, for me, it's a polymer blend. Yes, it's a polymer blend. So in the last century, there were many works on thermodynamics of such systems, but they were synthetic polymers. That's the only difference. But they are polymers, they are macromolecules. And the thermodynamics is the same. So Florey-Huggins parameter you can determine for your systems as well. So I do not understand why people invented this new label, because it's a polymer blend, and the emulsifier is a compatibilizer that we had for the polymer blends. So I know that you read a lot about it, so I'd like to hear your point of view.
The name, water emotions, right?
This
Why?
concept, it's a very old concept with a new name. Why?
Okay, so I have read that these water emotions was they received this name not recently, but like in the 2000 year and something, I guess. Because as you said, so far these systems, they were called the mixture between two aqueous incompatible phases, and just that. And that's what you're trying to say, that they really are. And there are some people, I have seen some articles that they don't use water emotions, and this kind of makes our work harder, because we have to search in the Science Direct, for example, two different terms, because if you type water emotions, a lot of articles will appear. But if you type mixture between hydrophilic and compatible polymers or polysaccharides in solution, other articles will appear. So I agree with you. The water emotion term is not the only possibility to call these systems. And I guess that's because an emulsified phase is formed. You have the similarity between with you have the similarity with oil in water emotions, because they form emotions,
Yes, but you
droplets.
have the same. You have the same. If you have two polymers and you melt them, melted state, two polymers that are immiscible, you get also spherical phases of one polymer dispersed on the second one.
Mm-hmm.
So there are so many plastics that we use in the cars, automobiles industry use a lot of incompatible polymers, but they are compatibilized by a block copolymer and so on. It's the same. I do not understand the need for a new name. It's really very strange.
I see your point. I can see your point. I agree with you. It
Yeah,
would be easier to have just one term.
yeah, it's just an immiscible polymer blend, and the solvent is water. But it's the same as we had in the last century for synthetic polymers or melting polymers. So it's I I'm sorry, but I think it's really a trend, and someone wants to get famous due to these names. I don't know. For me, it's really very, very strange. but it's okay. Just wanted to hear your point of view, because as I know that you read a lot of papers about it. So then, when we go through the equations, I did not understand the equation 6. Maybe you could check it. I know Dixon is a very well-known researcher. He's very good. But this equation is really strange in your case. It is the Young's equation, you know? It is exactly the Young's equation for contact angle of a liquid on a solid surface. And it does not hold for your system. So I did not understand it.
Actually, it's hard to test on our system, I would say, because
of course we don't have any significant facial tension. It's very low.
Yeah, it's very low.
Had commented on this. So it's another thing that the people create some situations that I'm sorry it does not hold, because the contact angle of what?
Yes, the interface is broad and it's hard to measure the contact angle. I agree with you. The interfacial tension is also a difficult parameter to be measured.
My point is that equation 6 shows that you have two phases. It is the Young's equation. That's my point. And for Young's equation, this theta, it is exactly the Young's equation. The theta is the equilibrium contact angle of a liquid droplet on a solid surface. Okay? So the liquid would be the phase B. The solid would be the phase A that you have in your equation 6. So who is the phase A and phase B in your case? I didn't catch that. I didn't understand it.
The phase A and the phase B would be the two dispersed and continuous phase, right? No.
You have two phases, A and B. Phase A is?
It depends on which is the dispersed and the continuous phase.
Okay, so you are looking at two phases, yes? But if it is a spherical, what is the contact angle?
The contact angle is the one that the particle has with...
But there is no particle there. You have two phases, not 3 phases.
Okay.
That's the point.
I see your point now.
So you have the water, which is the medium, okay? Water is the medium. It's like air in the contact angle for the traditional contact angle. Droplet solid. It's like the air. And you have the liquid. The liquid would be, for instance, Xylo Glucan. And then you have the solid. And the solid would be the Amylopectin phase. So what's the point? I don't understand. It's spherical or it's flat. So there is no intermediate situation. So I don't know. I didn't understand it.
Okay, I guess I can make better research about that. I have seen it in other articles. I think the reference is the same, although, and I could check this information.
Yes.
And I agree with you. It's a kind of a hard thing to assume to water or incompatible uh, polymer mixtures because it's hard to measure the contact angle. For example, even for protein particles, it's hard to measure the interfacial tension. Although it's possible, it's hard.
Okay.
And
But
I see it.
then you have the particle in one phase,
Mm-hmm.
particle in the second phase. But here it's my point is the equation.
Mm-hmm.
The equation it it is the Young equation for another situation that does not hold for this situation. That's my point. Nobody uses this equation for oil and water emulsion because it does not hold.
Mm-hmm.
Yeah.
Yes, I have never seen this equation for oil water
Yeah.
emulsions, mainly for water emulsion.
Yes, because if they are miscible, then the gamma AB is the same as gamma A minus gamma B.
So I guess that's the point because there are several studies that show that even though the interfacial tension between these systems is low, is really low, when the particle enters the interface, there's also a reduction in the interfacial tension term.
Yes, and that's my next question. Uh, do you think that it is really a reduction? Interfacial tension is the amount of force that you have at work per area that you have to do to increase this area. Okay?
Yes.
So to increase this area, we have to reduce the intermolecular interactions that are playing this interfacial tension. Yes? Do you really think that the particles reduce the interactions that we have, um, AMP, MP, or Xyloglucan, or is it just like a physical barrier that you build around these domains? And this is just a physical hindrance. It's not a chemical action. You are not you're not perturbing the interaction forces at the interface. I, I don't know. Did you think about it?
Mm-hmm. Um, you want me to give my opinion, right? Okay, so
Yes.
I would say that, well, I agree with your opinion that it might be just a physical barrier because the first studies about the water-water profile interface, these first studies, they showed that it is a solvent-rich interface. It's very likely for the particles to migrate to there and stay in there because it's a favorable situation for them.
Because the chemical potential there is higher. At
Yes.
this layer, at the interface, the chemical potential is higher.
Mm-hmm. I
That's why
agree.
I migrate, and that's my opinion.
Mm-hmm.
Exactly because of what you said, because you have a region which is richer in water and solvent.
Mm-hmm.
That makes the chemical potential higher, and that's why they migrate
Mm-hmm.
to this area. But then That's it. If it is polymer A, polymer B, polymer C inside, it doesn't matter because they are all hydrosoluble, okay?
Mm-hmm.
So then I ask you, do you agree with this idea?
Do I agree with what? With what you just said?
Yes, with this idea with the chemical potential.
I agree with the idea of the chemical potential, and
Then we go further.
okay,
I will ask you further. just to just make
just
some
just
assumptions.
let me finish, okay? Because I agree with the idea of the chemical potential that is higher at the interface because you have a solvent-rich interface, especially if you had charged polymer, it would be even higher the potential at the interface. I have seen some authors that discuss that. Yes, it
Chemical
was.
potential is not the same as electrostatic
Yes,
potential.
it's different. Okay, I agree. The concept is the physics the concept is different. Yes. Okay, but the chemical potential is higher at the interface, and I agree with that idea. Although the particles might migrate to the interface because of their ability to form just a physical barrier between the droplet and the dispersed phase. Although this happens, I do not exactly disagree that there is a reduction in the interfacial tension because even when you consider for example, the dilution effect, when you add a particle to the system, when you add a particle to a system and then you preparate another solution of polymers without particles and they are at the same concentration, but one has a particle and another one doesn't, there is a reduction in a significant reduction in the interfacial tension, even though they are really low. We actually tried to measure it because there we don't have a spinning drop tensiometer. That's the equipment that I saw that is used to measure these properties. But there is an approach to measure the droplet relaxation time. You apply a force to the droplet and
Right.
then you distort it, you see the maximum radius and then you check how many time the droplet takes to go back to the initial ratio, to the initial conformation. And this is proportional, of course, to the viscosity of the system, which must be taken, but this is proportional to the interfacial tension of the systems. And there are some formulas that relate to these parameters. And another student of mine, he did it for microgels with one or the other phase, and he saw a significant, because he did it several times, he had to measure like 30, 60 droplets for for each measurement, but we could observe some reduction. And this is not the first time that it was done for other systems. It was done also using theoretical models. I guess the name was, the method that they used it was science. I forgot the method now. I'm not gonna say, but it has been calculated theoretically for polymers that have, for water emulsions, the reduction of the interfacial tension. So I would say that the chemical potential is higher at the interface, but I cannot disagree that there is a reduction in the interfacial tension term. So this is it.
Yeah, the question is, it is already very low. Do these decrease, this incremental decrease, is it really the driving force that that causes these effects that you see? That's what I thought, that I would like to discuss with you. It's a little bit provocative. You understand, yeah?
Of course, yeah, sure.
And in this sense, Bianca, Xyloglucan and amylopectin, they have chemically they have similar structures. Why they behave so different when you put the same particle? Because you have situations where the particles goes to the xyloglucan, you have situations that they go to the amylopectin. So I didn't understand it. And the charges, you have uncharged polymers. The charge should play no role. So for me, it's everything a little bit tricky. I didn't understand.
Okay, so the they are not charged. I agree perfectly with you. And I check it, and there is not much scientific discussion about interaction of protein with neutral materials like polysaccharides that are neutral. Although there is there is a possibility that the structure of the materials, although they are both neutral, they present some differences in their structure. For example, the amylopectin is a highly hydratable material from the starch fractions. It's the most hydrated one and it interacts with the water. And xyloglucan is too a hydrophilic material, although it has already been shown that the structure of xyloglucan that is formed by a glucose chain, a main glucose chain, sometimes it's a hydrophobic um, chain, and sometimes the xylose units they collapse into the glucose units. And what makes the xyloglucan more hydrophilic is the galactose units. So we actually evaluated if the three xyloglucans had the same ratio of galactose per xylose and glucose too, because this is a very important thing when you analyze the solubility of these materials, because what determines if the xyloglucan will be soluble is the galactose ratio. Another work from our group even showed that when you reduce the galactose units per molecule, you increase the hydrophobicity of this molecule. So they are both neutral, but there are some differences in their affinity with water, I guess.
Mm-hmm. Yeah, I think it's a nice approach, because when we look at the structures, so the charges cannot play a big role, but maybe the hydrophobic part of the proteins might have some van der Waals interactions, hydrophobic interactions with the hydrophobic part of xyloglucan. Xyloglucan is not so easy to dissolve. It takes a little time.
Yes, you have to leave it like at least 12 hours.
Yeah, I know. It's not so that hydrophilic. So I think it's a nice approach to think about the hydrophobic interactions.
Mhm.
And not so about the charges, because the
Yes.
charges no. And then when we are talking about the charges in your experiment with the um, you varied the ionic strength, so at point 1 I ask you if these particles are stable, because there is no variation on the zeta potential with the pH. Yes?
Yes.
it's very low.
Mm-hmm.
So I'd like to ask you if they were stable.
No, they aggregate.
They aggregate.
They aggregate. Yes,
And
but
what? Yeah.
although I think that the viscosity of the emulsion, because I prepared everything with salt. I prepared the amylopectin dispersion with salt, and then the xyloglucan dispersion with salt, and then I added a little more salt in water so that the particles, because let me explain it better. When preparing the emulsion, I weighed the amylopectin and then the xyloglucan, but it's not the amylopectin, it's a solution of amylopectin, and then a stock solution of xyloglucan, and then I add a little bit of water to reach the desired concentration of the polymers that I showed you, and then I weighed the particles. Okay. And the mass of the particles that I add, for example, for a 3-gram emulsion, I weigh 0.03 grams of particles in each emulsion, as they are in a concentration of 1%. And what I did was to weight the particles in water. The particles weren't in salt, they were in water. And then I added a little bit more salt concentration in the water fraction that I weighted. And I think this made the particles stable until they were added to the emulsion. And when they were added to the emulsion, I guess that they aggregated because, of course, there were no attractive or repulsive potentials at the shear plane at the zeta potential. The zeta potential was kind of screened, and I guess the particles, they migrated to where they originally belonged, because the microgels that firstly interacted with the amylopectin phase, now they were at the amylopectin phase, but they were really aggregate. I think I can show you on the slides. Are you seeing my slides?
Yes.
Yes, okay. So here we observed that this is the experiment without any salt concentration, okay?
Mm-hmm.
So here we could see, for example, the microgels, they were at the amylopectin phase at pH 6, because this has microgels, while this is only a background fluorescence that we can adjust, of course. But although there is also, okay, a microgel here, but the microgels, they place themselves at the amylopectin phase, for example, at pH 6. And when we went to check the emulsion with the salts, the particles were here also, but they were aggregate.
Mm-hmm.
This is the mixing, sorry. Just a minute. This is, okay, but that's the same thing. For example, at pH 6, the microgels, they are here at the amylopectin phase.
Mm-hmm. Yes.
And they are not dispersed, they are aggregate, and that's probably because they are not stable.
Mm-hmm. And I asked you about this because of the last question of Professor Anwesha. Yeah. Most formulations, food formulations, they have high ionic strength.
Mm-hmm.
And sometimes they add salt also because they wanted to prevent microorganisms and so on. So then, if you think about this application for food, then maybe you should think about what you could do, because charges are a little bit tricky, isn't it?
Yes.
I saw that you are thinking about pay, yeah, to coat with pay with polycation. I saw in your future ideas and so on, yeah, perspective. But it's also a problem, yeah, when we have salt, and that's just a comment. But I would like to finish here. I think that you answered very nicely my questions. I'd like to thank you, and thank you, Hilton, and congratulate you both for the nice work. And I wish you all the best.
Thank you
Thank
so
you very
much.
much, Bianca.
Thank you very much, Professor Denise.
Professor Denise, I would like just to say few comments. First of all, I think we need to rewrite some parts of the equation 6, because when Bianca demonstrates the cosine of theta, she's talking about the difference of interfacial tension between the phase 1 and 2 and the particle, divided by the interfacial tension between the two phases. So I think we need to adjust the equation. Maybe this equation is broadly used, including for other systems, has oil and water. We have including a variation of these equations for other shapes, for example, rods or spherical spheroids or something like that. But we need to solve it to erase this kind of dark part or something like that.
Hilton, my comment was because sometimes we use an equation without thinking too much about it. This is a classic equation, 200 years from Young, for a completely different situation.
Yes.
And then sometimes we see something published, and sometimes it's not perfectly describing the situation, but this mistake is reproduced by other authors.
But I think
it's maybe not the case. I'm just saying that I also ask my students, do you think that this equation really describes your system? Did you think about this equation? What this equation means?
Yeah, I think it is really limited to explain completely the phenomena, and we discussed it a few months ago in the João Pedro thesis. We are discussing about the same. The equation is quite limited and can bring some very factors that could be analyzed and associated with the stabilization of these emulsions. But I think what we need to do is to insert the derivation of the equation. I think it will be much better to understand how the origin of this equation and how we can interpret it more clearly. I know that we just insert the equation has how can I say, has a classical equation, as you said, to interpret few parameters, has the radius and interfacial tension and the wettability of the particle at the interface, because is that what we are looking in the cosine of theta, and it's just that. Another question is about the chemistry of these interactions. I would like to say that in the case of Xyloglucan and Amylopectin, we have some kind of chemical interactions. For example, the professor gave us a very nice idea to study also the hydrophobic interactions. But at the beginning, we are thinking more about as the particle is positive below the isoelectric point, we start to think about the interactions between these protonated amino acids, and the acetal groups of the xyloglucan that are really more exposed. And we found some studies from the University of Harvard. They found that including PAO or PEG could form some kind of interactions with positive particles in several simulations. So because of that, we start to think about some kind of interactions between these materials and not just physical barrier. We saw, for example, at pH 5, we can start to see an adsorption of this protein in the the particle. We can form some kind of coating of the particles with Xyloglucan. We can measure it. We can analyze the particles, and this process is completely reversible when we change the pH. So we have some kind of interactions that we need to study and deeply with the continuation of the Bianca study. And I think it's that I need to complement if just to. But thank you very much. I think the professor usually put us to think a little bit more. Thank you very much.
Yes.
This is
A
very
lot
nice.
more.
We like this. I think it's a huge contribution to our group, and we would like to say in name of my group, my research group, to you. That is always you are always contributing positively to our research.
It's my great pleasure.
Thank you very much. Professor Eduardo. Let me just find him here.
Oh, can you hear me?
It's a
Professor
bit
Eduardo.
more.
Can you hear me?
Yes.
Yes.
Oh, Mr. Frau, thank you for the invitation. It's always a pleasure to to have an opportunity to learn uh, your work is very, very deeper. I I would say that with a little more results, your work could be transformed in the doctoral thesis instead of a master science thesis. So, congratulations for your amount and your quality of results. It's a pleasure to see your progress. I am happy. I am very happy with this. I have some comments about the writing style. I will. I am not say about this now because there is a long list. I will send the file, the PDF edited file. I think it's more practical than to set point by point. One point that I would like to highlight is in the first page of your work, in the title or the front page. I think it's the second page. You wrote thesis presented to postgraduate program and comes in the sector of exact science of Federal University of Paraná. I think that proper names should not be translated.
Okay.
I think because I have a curiosity about your name. What means Hazt? Do you know?
No.
I use the Google Translate in several languages. Hazt means neblina.
Imagine Bianca Neblina.
It should be strange. So
Yes.
I
agree.
think I think it's not be translated.
Mhm.
About your right style, I suggest you, as I said to João Pedro last time, to use a software called the Grammarly.
Okay.
It's very, very useful to write in English because further to corrections in preventing typos and something else, it's very, very rich to present some suggestions to enhance the style and to correct some problems with grammatical and so on. So I suggest you, if you plan writing English, of course, my congratulations for your courage to to write in English, because I think it's very, very more difficult than to write in Portuguese. But I would say that there is a long road and that you started, but there is very, very enhanced that I am certain that you can get in your style. About the thesis, some comments that they were not clear for me. First time, the equations 2 and 3 on page 23. Equations 2 and 3 are related with equations 4 and 5. I mean, one is for spherical systems, 2 and 3. And 4 and 5, 2 elliptical or something not spherical system. They are related.
Yes, these equations are related. I could say that equations 4 and 5 arise from equations 2 and 3 because the parameters A and B, they are related to the particle morphology. You have, I think I wrote the A is the value of the largest half aces of the length of the particle, and B is the smallest. I think I could introduce here a figure. I think you suggested it in my qualification exam, but I didn't have time to put it here for the final version. Maybe a figure could help understanding this.
So if equation 4 is related to equation 2, because the 4 is related to equation 3. There is the subscribed G way. And if A equals B in a spherical model, could you put in your screen, please? I think it's easy to think about this.
Just let me open it because it wasn't opened. Oops. Here, the equation 2 and 3.
So
and the equation
the equation 4, if E, A, and B are equals, the term inside in the fraction should be 0. Because it's 4A and B, A over B minus 1, A over B minus 1 is 0. So the equation 4 transform in equation 3. I could not understand the same for equation 5 to transform in equation 2, because there are the same index. I think
because if this term is 0, then we have only this, right?
In equation 4 or 5?
5.
5. But which term is 0? Because after cosine theta, A over B, it's 1. So the equation 5 is delta G is delta G dy plus 4 times gamma, 4 times P,
Mm-hmm.
B or A square, doesn't
Mm-hmm.
matter, cosine theta. But this equation is different from the equation 2.
Yes. I think I need to
So,
recheck this
so
equation.
it's some strange for me.
Mm-hmm.
And of course, equation 6. I didn't understand too, like Professor Denise, which are the labels for A and B. But
Mm-hmm.
let me find it. But when you say the change in free energy negative whenever uh, absolute value game gamma PA minus gamma PB is lesser than gamma AB, but always gamma PA minus gamma PB needs to be always lesser than gamma AB. Because if the numerator is bigger than the denominator, it should will be greater than 1. It's impossible. Physically, it's impossible. So I didn't understand this whenever, always, ever.
Mm-hmm. Yes. Maybe the word here could be changed. Yes, I agree with you.
And only a detail in figure 2, if you put here, please. I lose my
Sorry, I'm not understanding.
figure 2, please.
Uh-huh.
It's a beautiful picture. I guess you made it. But I
Mm-hmm.
found it strange because when you amplify certain region, uh, normally not the when you put that the small part and turn it bigger, uh, it's it's seems that you're trying to amplify,
Mm-hmm.
but the pictures the amplified picture is very different from the little picture.
Mm-hmm.
So I because this part I think here in the amplified picture should be the details in the small picture, not a different picture. I suggest you to
Yes.
put them apart in picture A and picture B
Mm-hmm.
with different informations.
Mm-hmm. This is the ternary, and this is a two aces phase
Yes,
diagram. Mm-hmm.
yes. Um, about tamarindo. When you say that you bought tamarindo in Curitiba market,
Mm-hmm.
I think important information is when you do this, because in Brazil we have a very mainly in Curitiba we have a very odd weather. So I think I'm not sure, but there are difference between tamarindo in winter and tamarindo in summer and so on. Uh,
Yes.
See if anyone try to reproduce your work. and found different results, I think it's important information to be placed. So I
Mhm.
suggest you. I'm not sure if is there a study about the difference between results in winter and with seeds of winter, seeds of summer, or I don't know. Do you
I
know?
have I have never seen about differences in the winter or in the summer. I bought them in the summer. It was in the beginning of 2020, January, exactly 2 years ago. And but I can tell you for sure that there is a difference between buying seeds now or not only in the if it's a summer or a winter station. Also, if you are looking at differences in the solo composition, and there are many things that could change the molar mass of the tamarind fruits. For example, the Xyloglucan 1, and that's the main reason why we followed the experiments with the Xyloglucan 3, because it's a commercial sample, and there's a lot of this commercial sample in our lab. So the results are probably easy to reproduce.
Okay.
And for when you bite, and that's why we decided to keep going with the Xyloglucan 3. But the Xyloglucan 2 was extracted, and probably if I do it again with another another tamarind that I buy now, it's January, the molar mass will probably be different, because I this is really common when extracting polysaccharides and working with them. Some differences in the cultivation can lead to different molar masses and macro and all the macromolecular parameters.
So I think it's important to have to have this in mind. Another question is about your dye usage. Is do you use it rhodamine? I think,
Yes,
but rhodamine is not the only one dye. It's a class of dyes. There is rhodamine B, rhodamine 6G.
6G. Uh-huh.
There are several. So uh, this detail could be important or not, but if someone try to reproduce, I think it's better to be specified with rhodamine was
Yes,
used.
I
I think
agree with you, because their wavelength absorption is different. Even being all
certainly
rhodamines, they are different. I agree with you. I think I need to write that it was the rhodamine B.
yes, because your work uh, possibly uh, will be used for starting another works in other for other students. So the first mission should be try to reproduce Bianca results, and the guy or the girl will be lost because conditions were different.
Mm-hmm.
And uh, you say about radius of durations on page 49. It's let me try to fix this.
Okay.
Let me check.
For the microgels, right?
Yes,
Mm-hmm.
uh, these values were measured for you, or you calculated. How do you get them?
No, no. Actually, I only compared here that Okay, we had hydrodynamic radius, and this author named Carla Mova found radius of duration. That's two different ways to measure different properties of these nanoparticles. I think what I meant here is just that the size of the microgels that this author found was similar to what I found. And then I could compare the protein to particles conversion, which was 85% for her or for him. I don't know if it's for
Okay.
this author, and for me it was 84%.
Okay. So,
But I can rewrite the sentence to make it clear.
you showed in your results that IP, I think it's isoelectric point change with the ionic force. Do you have some explanation for this?
Yes, I have. So I know that the isoelectric point is the point where you have it's the pH at which the zeta potential charge is 0. And
So you have a positive and negative charge in the same molecule.
yes, both positive and negative charges at the same molecule. And then when I added salt, it was sodium chloride, to the system at 2 concentrations, I observed that I had a small variation in the isoelectric point. This could be attributed to the fact that when I have counter ions adsorbed at the particle's surface, the size of the, how could I say it? Let me think a little bit. The size of, it's not the Debye length. I think it's the Debye length that we call the size of this. Just a little bit. Let me think in the answer.
Try in Portuguese if you don't remember the name in English.
Camada. I can't remember the word camada. Size. Layer, yes. So when we have the presence of salt concentration, the electric double layer is compacted because we increase the salt concentration, and then the particles, they migrate. For example, if we are talking about an electrophoretic measurement of the zeta potential, then the particles, they migrate with a slower rate to the electrodes. Yes. And so when we are in the presence of salt concentration, we have that the zeta potential is screened.
Okay.
And I observed that the isoelectric point, it was a little different from what I had previously found when I performed the titrations only in water, because I did it several times. I did it 3 times for each sample in each salt concentration at least, and I observed slight different values, and I hadn't observed this when I performed the titrations only in water. And I think this is mainly because when you are working at the region of 0 zeta potential, the equipment is not so specific. Stable, yes, because the particle is not stable. The equipment is not made to measure nothing. It's made to measure something. And then when we screened the zeta potential, we had this error in the measurements. I think it was because of that. But in the literature, it's very discussed, this effect that adding sodium chloride to proteins in a general form, it you can change the isoelectric point by adding this sodium chloride because of the absorption of the other ions at the particle surface. And there is also the discussion about the difference in the isoelectric point and also the isoionic point when you add an ionic strength to the system. And I think for the isoelectric point, some authors they observe that it is lowered, and then when you have the isoionic point, it's a higher isoionic point in the presence of bigger salt concentrations. So there is this variation between these two parameters, and this was our initial goal when adding sodium chloride to the system. We didn't know what was going to happen, but we imagined that we would have a slight change in the isoelectric point, because with a change in the isoelectric point, we could prove our theory that the protein charge is important in the interactions with the Xyloglucan acetalic bonds, and that's why we did this experiment. But in the end, we got a pretty good result about the repulsive potentials of the surface of the particle.
So may I suggest you to write some paragraphs to emphasize your ideas here, because it's something that could be more discussed. I know the time is limited, and it's always a good idea to, but it's also have a whole screen of the system. So I think this part should be interesting.
Mhm.
So I have no more question. I wish thank you for the invitation, you and Hilton, and I congratulate with you because your work is very very beautiful. I like it very much to read it. So thank you.
Thank you
Thank,
very much, Professor Eduardo, for all your contributions.
thank you very much, Professor Eduardo, again here helping us to discuss and to improve our work. I would like to invite the jury to migrate to this link I send now in the private chat here. Please, if you can go to that virtual room, because we need to discuss about the Bianca situation. I think it will take like few minutes, and after we return here to give her our decision.
Okay. Do you need to get out of the start leave?
Yes, yes,
I think
yes,
yes. Huh?
yes.
So
Bianca, you can stay here, okay? And the audience also.
Pleased to meet you, and I kind of agree with all your questions. I
Mhm.
didn't want to probe because they were difficult, I thought, so I just moved away from the equations because the first question I asked, she started with a bit, so I thought it would get the end. And it's difficult.
Yes.
Yeah, exactly.
And
Yeah,
Onesha,
but she has done.
yeah,
Yeah,
and
I think for me as a uh, master's thesis, it's beyond imagination what she has done.
okay, thank you very much. Yeah.
I gave it very good work and published as well. Very clean. The quality of data generated is very nice. Base diagram.
Well, I will just say a little bit about my impression. I'm sorry. I was just here, and I just forgot to click on the button to put me online here with you.
Professor,
Well,
we can hear you here.
okay.
You might mute your microphone here in this room. Não que eu não quero ouvir, né, mas...
let me just wait for Eduardo, Bianca, and I will let you know the decision. Professor Eduardo is here. Just so, Bianca, I will let you know about the decision of the jury. And the board chair initiated the reads and defined it by the faculty and program. And after the remarks of the members and the examining committee and the respective response were addressed, the final evaluation of the examining board were read, which was decided by approval. So you are approval. You receive an approval in this process. Congratulations. Was really nice to work with you during this period of time. You received a lot of good impressions and some suggestions that I will let you know later. But thank you very much for this interaction with my group and with my in this field that is really an important field in our lab actually. So you are a very dedicated and a person that is involved in different aspects in our lab is actually is one of the key person in our lab. So it's really nice to work with you. I really have you as a daughter, and you know, in Brazil we mix the things. So you're really like my daughter here in the lab. Really nice to stay. I don't have words to say in English. I start to be nervous, so I will let you know later what I think about you in Portuguese.
Congratulations, Bianca. Very well done. Huh? Very well done. Very good work.
Congratulations, Bianca.
Congratulations, Bianca. All the best to your future.
Okay, I would like to say thanks for your time that you spent with evaluating me. Professor Anwesha, you made some very important questions. Thanks for your time reading and evaluating this work. Also, Professor Denise, you always make some very interesting observations that always make us think, and it's a pleasure to discuss our scientific work with you. It's always a pleasure. Also, I would like to say thanks to Professor Eduardo. You made some very important comments, and these comments will certainly improve our document. Thanks also for your classes that I had with you. They were great, and I learned so much with you. And last but not less important, Professor Hilton, you're the biggest inspiration for me. You're my scientific father. And thank you really, really, really much.
Right, so we can just, after I will just send you to the jury the document to sign. Unfortunately, in Brazil, at the Federal University, we still have to sign the document or put an electronic signature. Unfortunately, I will send you the document with the approval. And you just need to sign it and send it to me, send back to me. Okay? Thank you. Bye.
Thank
Bye.
you.
Nice to see you all.
Bye.
Bye.
Bye bye.
Vou encerrar então a transmissão, pessoal. Obrigado para quem ficou até agora. Bianca quer ficar?